Okay, so last time we talked about modern atomic theory. We talked about where electrons are, and that's really what this chapter is all about. This chapter is about where the heck can you find an electron around a nucleus, a much more specific description than any of these previous ones. John Dalton talked about atoms as balls. We've talked about Lord Kelvin and his plum pudding model, just nipping the electrons off. Rutherford really went to the nucleus. He used that gold foil experiment, made the nucleus really tiny. He didn't make the nucleus tiny. He discovered that the nucleus was tiny. Then we have these two, the Bohr model. The Bohr model is pretty good. This is probably the one you used, had like electrons on different energy levels. And it's pretty useful. And we talked last class about how if light hits one of these electrons, what might happen to one of those electrons if it gets hit? Gains energy. It gains energy, doesn't die, no. It gains energy and it gets excited, and so that electron can't stay on that energy level. It might hop up to a higher energy level, and it'll be moving around this energy level with more energy, but eventually the electron's going to get pulled by the protons back down to the energy level it left. And as it does that, it's going to have to give off what before it can drop back down? Energy. It's going to have to give off energy, and we see that energy as light again. But you could excite these electrons not just with light. How did we excite the electrons last class? We used fire, right? We burned some sodium, potassium, strontium, copper, and they burned different colors because we were exciting these electrons in their energy levels, and they were hopping up to higher energy levels, but then as they dropped down from the excited state down to the ground state, they released energy. But we saw the energy. And I think copper was green. Remember seeing the green one? Yeah, it was pretty. You're allowed to talk. You don't just have to shake your head. And then, right as we were kind of like getting the last bit of class, we got into the quantum or wave mechanical model. And it describes electrons more precisely. It does it in four areas. It talks about energy levels, talks about sublevels, discusses orbitals within those sublevels, and then that the orbitals have to have a certain type of, the electrons have to have a certain type of spin, right, electron spin. And we discussed them in four different areas, and that's probably what we need to kind of get back into today, because that's drastically different than anything you learned before. And we wrote out configurations. Your homework was to like write out configurations like 1s2, 2s2, 2p6, 3s2. But a lot of people didn't understand. Who didn't understand what they were doing when they wrote that out? Let the record show that there's 15 hands held up. And therefore, we need to redo that because you guys don't feel like you know what you're doing, but you're just doing it. How many people just like wrote out random letters and numbers and were like, I don't know why I'm doing this? Let the record show only one hand. It's Jennifer's. No, there were like 15 hands. So we talked about it, and we had this picture of people, and there was a lady in there, and we were surprised. And we did some math, but we're not going to be really focused on the math. We're really going to be focused on these last pieces, getting to it. We're getting to the wave mechanical model. What page are we on right now where the wave mechanical model is? 46? Okay. And so when we got to here, we talked about how physicists and chemists work together to figure out where electrons would be, and it's really difficult to describe where an electron is because they're moving so fast, and a guy named Heisenberg comes up with this uncertainty principle. It says you can't really know the location and the velocity of these particles. They're moving too quickly. So instead they come up with this idea of an orbital. And orbitals describe where electrons are with a 95% accuracy, which is pretty good because electrons are moving at like 10 to the 8th meters in 1 second. So about 100,000 to 400,000 meters in a second. So it's going to be hard to describe where they are. So they don't try to pinpoint them. They give an area or a region, and we call that region an orbital. So it's all based on a lot of math. How much of this really difficult math do you have to do? None. We really are kind of looking at the outputs of the math, which are pretty pictures, and you're not drawing these pictures, you're going to be writing representations of these pictures. This might be the configuration for neon. So neon has how many electrons? How would I figure out how many electrons a neon atom has? I would go to the atomic number on a periodic table. Go ahead and get your periodic table out. You're going to need that in order to follow along. And as you look on neon, you see it has how many electrons? 10. It has 10 protons and 10 electrons if it's regular old atomic neon. And the other thing we're going to use our periodic table for is on the back, there's something called Aufbau's order. And Aufbau is German. It means to build. So basically this order is the order in which electrons build up around the nucleus. And it's given right there. And I'm going to write down neon's configuration. This is neon, 1s2, 2s2, 2p6. And we're going to get into how to use Aufbau's order again, but the key part here is that the superscripts, right, these superscripts, add these together. 2 plus 2 is, plus 6 is, that's how many electrons neon has. The superscripts represent the electrons for neon. What do the other things mean? Good question, Nick. The other things, like this 1 and these 2's, those are the energy levels. So there's electrons moving around the nucleus on different energy levels. For neon, there's electrons on the first energy level, and there's electrons on the second energy level. And they have different amounts of energy because they're moving at different speeds around the nucleus. And that's what the 1's and the 2's mean, the large ones, the coefficients. What do the S's mean? The S's and the P's are what we call sublevels. And the sublevels are basically we're chopping up the energy level into smaller areas to describe it more precisely. And then the last thing that's not really represented in this configuration are the orbitals, which I started with the B. That's weird. The orbitals. And this drawing I have on the board kind of represents the orbitals, but wouldn't that be painful to draw? It'd be very painful to draw. So you are never going to draw a picture like that ever. And I'm using the capital letters N-E-V-E-R for never. We're never drawing this. This configuration represents this, and I'm going to explain it right now. So the 1s is this small sphere that's on the inside, and we're saying that in this small sphere around the nucleus, there are 2 electrons moving. S for sphere, all right? And then what happens if that energy level is full and you still have more electrons? You go to the next energy level, and you start filling up what comes next. So there's another sphere. And you can see on this picture, there's a larger sphere, isn't there? And so you're describing not only the energy level, but the shape upon which the electrons are moving around the nucleus. So the electrons are zooming around the nucleus, now farther away from it, but there's only 2 there. And then the P's can hold 6. They actually always occur in pairs of 2. They occur in pairs of 2, like there's 2 electrons, there's 2 electrons. This is how many pairs of electrons? This is 3 pairs. And so there is, let me do this in purple, I'll do it in orange, why not orange? So there's a pair of electrons moving in this orange orbital. There's a pair of electrons moving in these red orbitals. And there's a pair of electrons moving in these purple orbitals. And if there's 3 pairs of electrons, that's a total of 6. And so when we write configurations out, we're describing where they are and what the space they're moving around in looks like. Okay? It would be like to say, right now Nick's in a classroom, and you have a visualization of what a classroom looks like. Later on, Nick's going to be in the cafeteria. Do you have a visualization of what the cafeteria looks like? Later on, he's going to be in the bathroom. Do you have a visualization? Yeah, you don't want that one. But you have a visualization of each one of those shapes, that space. That's what S and P, and then later on, what are some of the other sublevels called? There's an F, and there's a D. And those are different shaped spaces around which the electrons move. Do you follow me? Now, are you always going to have off-Bose order? Yeah, it's on the back of the periodic table. And that's the order in which it always fills up. Let me get to my off-Bose order. Oh, and so I'm going to scratch those two out. So look, there's really 1, 2, 3 shapes for the P's. Okay? X, Y, and Z axis or something like that. And that's 2, 2, and 2, so 6 electrons. These are the D sublevels. And I think you can really start to appreciate why we never draw these by hand, can't you? This is only 5 shapes. It looks like a lot more than that, doesn't it? But it's 5 separate shapes, or 5 orbitals. And if an orbital can only hold 2 electrons, there's like a fly flying around right here. I just recorded that. Awesome. If there's 5 orbitals there and they can only hold 2 electrons, how many electrons total would be in the D sublevel? 10. Does that concur with what's on Aufbau's order? 10. There's space for 10. What if you only had 4? Well, you only use 4 of the 10 spaces. What if you had 9? Well, then one space isn't completely full. And it is possible to have a half full. I mean, like, can't you go to the cafeteria by yourself? Have you ever been in the cafeteria by yourself? It's weird to be in such a large room by yourself. But you could. The same thing with electrons. You could have all of this space and only have 1 electron in any of them. And that's very common on the periodic table as we go through the periodic table. That's a really bad drawing I drew. And then, so here's Aufbau's order. It's incredibly useful for doing electron configurations. You could do any element. We're going to do a really long element. And then we're going to show the shorthand. Because we didn't do any of the shorthands, did we? Did we do noble gas configurations? No, I don't think we did. You're going to like noble gas configurations because you don't have to write as much. And who doesn't like not writing as much? That was like a double negative compound sentence. You don't know how to answer that, do you? It's a great example of bad questions. So let's do polonium. No one ever talks about polonium. Let's do polonium. So you've just been asked to write the electron configuration for polonium. Step 1, find polonium on the periodic table. He's a Po man. You should be able to find him. Yeah, I'm recording the bad jokes. I know, that's just so embarrassing for you. These jokes are all brought to you by Michael Smith. He didn't write the jokes, he's just endorsing them. How many electrons does it have? 84. So it has 84 electrons. So you are going to go through Aufbau's order. Just for 2 seconds, just watch the pen. All right? You're going to go through and you're going to go 1s2, 2s2, 2p6, 3s2. And the pen is moving down the arrow on the diagonal, right? And when it gets to the end of the arrow, what's it do? Goes to the next arrow, starts at the next arrow, and then you slide all the way through. And then you go to the next one, and you slide all the way through. And if you have to keep going, you keep going until you adds up to 84. Now this is a big one, and I've picked this one because right after this, we'll do the noble gas configuration, and it'll take way less time. Does that sound good? So let's do the long way, and then appreciate the short way after that. So here we go. It always starts 1s2, because that's really close to the nucleus, and those electrons, I'm going to cough right in the thing. That's going to be fun for whoever's listening. It always starts 1s2. The electrons are going to get pulled close to the nucleus, and they're going to fill up a small sphere. And the electrons are flying around in that small sphere. And then it goes 2s2. What comes after 2s2? After 2p6? After 3s2? After 3p6? I'm going to stop and count now because I've gone pretty far. I don't want to overshoot. That would be embarrassing. I'm recording this. So 2 plus 2 plus 6 plus 2 plus 6 plus 2 is 20, which is nowhere near 84. So I got to keep going. So after 4s2, after the 4s2, I'm going to hop over here, 3d10. And the third energy level does a wonky thing right there. It's like I was filling the 3s, I was filling the 3p. I'm going to hold off on doing the 3d and go back and do the 4s. It goes out of order. And I kind of feel like Aufbau's order is pointing out that it's occasionally off by a little. Oh man, I got a groan. I love groans. And so after the 4s gets filled, then it comes back and does the 3d. Okay, so it's a little off, and you're allowed to use Aufbau's order, and that's okay. All right, so 4d, 10, that would bring us up to 30. So I go 4p6, now I'm at 36. 5s2, 4d10. Am I even remotely close right now? This is 48. That's taken a while, isn't it? Then it'd be 5p6. After 5p6 is 6s2. After 6s, whoa! 4f14. The total now would be 70. Now, I'm not just magically adding these in my head. I actually just know where things are on the periodic table. So I'm going to teach you that in 2 seconds all, because all of this is hidden right in front of your face on the periodic table. I don't think we got into that either, but where am I now? 6p. But if I stop right now, I would be at about 80. Oh, I skipped one, didn't I? What did I skip? Oh, what an idiot. My teacher's an idiot. 5d10. Yeah, if you skip those 10, that's a big deal, wouldn't it? And here's where it was. I did 4d and then 5d, and now I'm in this area. 6p. Now I'm going to pause. So if I do the math right now, if I do the 2 plus 2 plus 6 plus 14 plus 10, I'm going to be at 80. Right now, I would be at 80. And I was told by the lady in the back with the blonde hair that I had 84 electrons in a polonium atom, right? So how many more electrons does polonium have? Only 4. How many spaces are there in the 6p? 6. But I only have 4 more. I have space for 6, but I only have, how am I holding up 9 fingers? That doesn't make any sense. I have space for 6 electrons, but I only need to use 4 of the spaces. So 2 of the spaces aren't being used. You got me? So we have effectively described where all of the electrons are for polonium. And what this says is small sphere, bigger sphere, weird peanut shapes, bigger sphere, peanut shapes, even bigger sphere, what those weird 5 shapes, a big set of peanuts, a bigger sphere, more weird peanuts. No, those 5 weird shapes. That's what we're describing when we write this out. Can you imagine why we're not drawing the peanuts and the spheres and the 5 shapes and everything now when you get down to here? That would be an insane drawing. Don't be that kid. I had that kid one year who thought I was asking for the drawings, and I'm not ever asking you to draw them. The hardest thing I'll do in terms of the shapes is say, what shape does an s orbital look like? Not draw it. What shape does it look like? And it will be multiple choice. Okay? Or the P's. But the D's are all weird shapes. And have I even shown you a picture of the F's? There's a reason for that, because they're even weirder, and there's still some disagreement about the final answer. So I promised you there's a shorthand version, because that takes a long time, doesn't it? So the shorthand version is called the noble gases. I want you to take a minute, look at your periodic table, find the noble gases on your periodic table. I think we labeled yours, didn't we? Is group 18 the one we labeled? All right. And so the way you do the noble gas configuration is you... where's my meter stick? All right. I'll just point with this then. So here's the element we're shooting for, and you're going to go back before it. Which noble gas has fewer electrons than polonium, but not drastically fewer? Would you pick helium? No, it's way too small, right? Would you pick neon? No. You would probably pick xenon, right? Because it has fewer, but not drastically fewer. And so when you write down, you can write down xenon in brackets. And when you write down xenon in brackets, how many does xenon have? How many electrons? 54. And so what you just did is you just took care of the first 54 electrons, which would be these that I just crossed through. So you don't have to write down 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. You don't have to write that down. You can jump to 6s2. You get to jump to 6s2. And what you're basically saying is polonium looks a lot like xenon on the inside, but the outside's different. And here's what the outside looks like. And that's all we really care about in chemistry is the outside. Because if an atom is flying through space, I'm going to pretend to be an atom. You get to be an atom too. Atoms are round. Here you go. There we go. If I'm flying through space, are my outside electrons going to bump into her, or are my inside electrons going to bump into her? The outside. They bump into each other. And so I only really need to represent what's on the outside because that's what's going to collide with other atoms. The outside has a special name. It's called the valence. The inside has a simple name. It's called the core. Something I need to work on. Yeah. All right. So, we don't think we touched on this much at all, if at all, did we? Well, electrons have issues with each other. First of all, they're all negative. So they repel each other, but they're not sitting still. They are moving. They're spinning. And so they interact in really weird ways. And since the next couple seconds aren't going to actually show on film, I'm not going to record the next 5 minutes. All right. So after that, so when electrons are moving around in these orbitals, S's have 1 orbital, P's have 3 funny-shaped orbitals, D's have 5 funny-shaped orbitals. They're spinning. And they have to have opposite spin. But since we're not going to make our hands fly around on the paper, and we're not going to draw woobly 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 things on the paper, we're going to use really complex symbols called arrows. This arrow's spinning one direction. What's the other one doing? It's the opposite. Boom. They actually used to have people draw an arrow in a circle for clockwise and an arrow in a circle for counterclockwise. But one day they decided that's wasting time. Why not just, it's still a representation. This is all a model of what we really think is happening. So what we have here is what does happen and what cannot happen. They cannot have the same spin. They can't be going the same way, and they can't be going the same way. They have to be going opposite ways. This is called the Pauli exclusion principle. The Pauli exclusion principle says, morning, how are you doing? Wait. So Pauli exclusion principle, what does it mean to exclude? If we're going to exclude Nick from having cake later, we're not going to let him have cake, right? Yeah, he's making a little pouty face right now, which is hard to tell from his regular face. No, he's a good smile. What it means is that if one electron is spinning one way, it excludes any electron that's also spinning that way. It excludes same spin. I kind of wish it would say it includes opposite spin, but it only says excludes. It's the Pauli exclusion principle. Okay? Has to be opposite spins. And then the other rule we're going to talk about a lot is Hund's rule. And Hund's rule I have down here. So let's say that there are electrons that are trying to take up orbitals. And we typically don't like draw the peanut shapes. Instead, we'll just have boxes that represent those shapes. And you can draw boxes. For many years, you've been able to draw boxes, right? And so these boxes represent those orbitals. And the P's had like a P peanut and a P peanut, and then one that came out of the board and went back in. But instead of drawing those, we have 3 boxes. Good? And then we're going to put electrons in these. So I'm going to put an electron in. There's an electron. Where would you put the second electron, do you think? If you had multiple electrons, is it going to go in the same peanut, or is it going to take its own peanut? I have a same and I have a same. What do electrons do to each other? Are they attracted or do they repel? They repel. Each of these orbitals is worth the same amount of energy. And so then the second electron, that was pretty fast. The second electron is going to go in its own orbital. A third electron is going to go in its own orbital. But if you have a fourth electron, then they're forced to share. And so the fourth electron would then start to double up. The fifth electron would double up. And the sixth electron would double up. And that's called Hund's rule. Hund's rule says when you're doing like the 3 P's or the D's, you have to spread them out before you can double them up. And this actually explains a couple of weird things on the periodic table, especially with those d orbitals. We already did noble gas configuration. So you have this drawing, right, in your notes. We're going to go down to this one first. Here's chromium. Whoa, whole page is moving. Earthquake. We have chromium's configuration. And what we would do is we would start with the lowest energy. This is an energy diagram or an orbital diagram. An orbital diagram for chromium. And when we do this, we're always going to start at the lowest. And in the 1s, that's too light. We would always start at the lowest. So I've got 2 electrons, and then I've got a lot more after that, don't I? So I start at the lowest, work my way up. How many are in the P's, does it say, for the chromium? 6? So the way you would do that again is you'd go 1, 2, 3. So I spread them out. That's Hund's rule. And then when I pair them up, they have to have opposite spin. And opposite spin is Pauli exclusion principle. Now, these all happen to be full right now, don't they? So it didn't really matter that I spread them out. It will matter when we move farther along in chromium. I think then we would do 2s2, 2p6, 1, 2, 3, 4, 5, 6. And again, these boxes represent those shapes you're never drawing. Okay? So that is a P, and a P. And then so there's an electron moving around here, moving around there, moving around there. I'm half full, started to double them up, take the other space and finish filling it up. Does it go to 4s2 next? Yep, 4s2. And then lastly it says 3d what for chromium? 4. And this is where it would actually matter, because chromium would go 1, 2, 3, 4. And so with this last sublevel, several of them are half full, and one of them is completely empty right now. It's supposed to be the word empty. We have 4 that are half full, one that is empty. And that really impacts how chromium bonds, how it makes charges and everything. Chromium usually takes a +2 charge. Sometimes it takes a +1 charge. Sometimes it loses these 2 electrons because they're on the 4th energy level, which would be the outside for it. And sometimes one of these guys just slips over there and only loses 1. So chromium can do a couple of weird things, which is why that transition area is such a pain on the periodic table. All right. And you have a couple more of these in the notes for 2 other elements. What are the 2 other elements? Sulfur and bromine. Okay, so I'm going to pause the video. You guys work out sulfur and bromine. Okay, it's pretty much the same idea, but the ending is different, isn't it? The ending is different. So I'm going to. So let's just do the last one up on the board here. Bromine. Bromine has 35 electrons, and so you go to Aufbau's order, and it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. But when we get to the 4p's, we run out of electrons. 4p's could hold 6, but there's only 5 left, so it's going to end with 4p5. And I had a good question from Sir Bill back there. Like, the beginning is all full. We're not going to ask you to do the entire thing. We're probably going to get focused in on just the interesting one. And the only interesting one really for bromine would probably be the very last one, because everything else is completely full. So your answer, though, should be, up, down, up, down, up, 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 down, 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 up, down, up, 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 down, down, down. And I'm doing this dramatically on purpose to illustrate Hund's rule, spread them out, Pauli exclusion, opposite spin. So up, down, and we're here. Now I got to get through all of those guys, and since there's 5, you go up, 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 up. And so theoretically, those 5 electrons are all spinning the same way in 5 separate orbitals, 5 separate shapes. And then they get crammed with the second electron, but if that electron's going to fit in there, they each have to be in the opposite direction. Why up first? I think it's because we want to be positive people and be up, right? Instead of downers. So we always do the ups first. They release questions for the SOL, right? And my least favorite question for the SOL is this question, because over on the side is a box with an arrow and another arrow, and I'm just making them opposite colors for no particular reason. And your job is to drag the arrows and fill in the boxes. Do you see why that's my least favorite question? They wouldn't do like bromine. They would probably just do, let me just eradicate all of the fine work I've done here. Feel free to pause it if you need this at home. If you had 3D3, they're expecting they would just, give you that and say, how would this element look in the 3D area? And so you would be like, I need an up arrow, and an up arrow, and those 2 are blank. And that's what they were expecting. And then they're hoping that somebody's going to do, not hoping, but then, kids might do this, and they're considered to be wrong. They're supposed to do the first 3 and leave the other 2 blank. Does that make sense? So, again, what are we doing? We're describing something incredibly complex. We're describing how electrons move around the nucleus. And, you guys are probably going to take physics next year, if you haven't already, or aren't currently, and you're going to, do labs and stuff, where, a ball is flying through the air at 15 meters per second. How far away will it land? And that's kind of tough to do mathematically. Just imagine if the ball was moving at 1,000,000 meters per second, attracted to, the nucleus and all that other stuff. The math becomes incredibly difficult. It used to be a phone. So we already talked about noble gas configurations. I think I have like the last example up there. You know, if you did barium, here's barium's entire configuration. But man, isn't that a lot easier? Just writing the final piece. So now here's the secret. The periodic table is organized in this way. Everything about Aufbau's order is actually buried in the periodic table. And I'm going to draw what is by far the best drawing of the periodic table ever. It's looking pretty good. Yeah, look at that. That's a square. Not bad. Okay. And then we're going to put hydrogen and helium. How'd I do? Not bad? I am missing something now. I'm missing these guys down here, aren't I? There we go. And so I'm writing it like there's 4 chunks. Like I've just cut the periodic table into 4 areas. And those 4 areas correspond to where we find elements that end with S, elements that end with P, elements that end with D, and elements that end with F. And check your periodic table. How wide is this part of the periodic table? 2. How wide is this part of the periodic table? 6. How wide is this chunk? It's going to take a little more counting, but 10. And then go down here. These guys are 14. That is an after-the-fact, meaning these guys are doing all this math and drawing loopity balloons and, woo, look at that, that's great. It accidentally corresponds with the periodic table. And that's awesome. To like have the periodic table in front of you for, 80 years and be like, yeah, this is how stuff's put together. It's great. We don't really quite understand it, but it's good. Let's put all this stuff in the same group because they're the same. And then Everett's always looking out the door. What was the last element we just did? Bromine? What did bromine end with? Like 4p5? Is it 4p5? Where's bromine? Bromine's like right here, isn't it? It is. It is 5 over in that section, isn't it? Starting with helium, how far down is it? How far down is bromine starting with helium? 4. So bromine, let me get this straight, is 4p5. It's 4 layers down, 5 over in that section. Isn't it? It's all hidden right there in front of you. So like when I do that stupid like 1s2, 2s2, 2p6, 3s2, I'm not like I didn't memorize Aufbau's order. I just understand that it's all hiding on the periodic table. So I look at the periodic table and I say to myself, 1s2, and I mentally put helium right there because it's hydrogen, helium, 1, 2. 2s2, 2p5, 2p6, 3s2, 3p6, 4s2, and then what happens with the D's? They're off, aren't they? It goes 4s, 3d. And so here's 3d up to 10, 4p, there's my bromine. And then it just keeps going. And I just mentally build based on the section. Now, where do these fit into the periodic table, the F's? Where do they fit in? Look at the periodic table. Look at the numbers of these elements. Yeah, they fit in like right here, really, don't they? And it usually has like a woo, woo sort of thing. And so you kind of go, bup, 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 and then back up here, which matches with Aufbau's order. Do you have to have how the periodic table is memorized? No, because you have Aufbau's order. But it's really nice to, instead of adding 2 plus 2 plus 6 plus 2 plus 6 plus 10 plus 2 plus 6 plus 2 plus 14, all that numbers together, just to find your end. So Natalia, pick an element, a big element. Tungsten, W. So tungsten is right here. So it's 1, 2, 3, 4, 5, 6 layers down. So these are going to be 6 S's. And these are going to be 5 D's. So 5D, 1, 2, 3, 4. It's going to end with 5D4. And so I would go to off-Bose order, and I know where to end. And we always start in the same spot with 1s2. So I'd say 1s2, blah, 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 5d4. Or even better, if I'm doing a noble gas configuration, every noble gas ends with a p6, except for helium. So it's a lot easier now, because like if I was doing bromine, what's the noble gas right here before bromine? Like argon or something? And so you could say argon. You could say argon. And argon would be 1s2 up to 3p6. How do I know it's up to 3p6? It's 3 layers down, 6 over. It's 3p6. And then I could say 4s2. Ooh, that's a 3. 4s2, 3d10, 4p5. Just the important pieces that come afterwards. So that's how the periodic table is organized, which is pretty cool. On accident, it actually explains what Mendeleev put down long ago. Key terms, valence and core electrons. When you think of core, what do you think of? Your abs, okay. I wish I thought about that ever. How about apples? Apple core is the inside. So we talk about core electrons. With this example here, everything that's in blue is a core electron because it's inside of the outside. What is the outside for this element? 6s2 is on the far outside. Everything else is inside of that. So the outside is called the valence, and the inside is called the core. And the valence is really the only exciting piece. The rest of it's kind of boring. It impacts the element, but it's kind of boring. All right, so that's Dmitri Mendeleev. Dmitri Mendeleev has kind of a sad story, which I don't need to record. So ionic size is really easy. If I take 2 electrons from you, are you going to get bigger or smaller when I take electrons away? Smaller. So when calcium's a +2, it's smaller because it lost electrons. What if sulfur was a -2? Be bigger because it would have more electrons. The number of protons aren't changing, and I think as the protons are the pull and the electrons are the opposite of that. So if you take away some of the electrons, the protons are going to pull on the remaining ones even more. If you add electrons, the protons aren't going to be able to pull on them equally, so they're going to be farther away. That's a really big periodic table. Okay. There are a couple of trends. I'm going to try something here. I'm going to steal some stuff from everyone in the first row. I'm going to steal this from you. No resistance. She didn't even fight me, did she? So easy. Let's see if I can steal from her. A little bit more resistance. Like there was like a friction, but I got it without really any effort. Now, okay, that was harder. I had to now, he doesn't appear to have a pencil. He's not going to fight me. Well, that's not going to follow. Periodically, things go wrong. And then I want you to not let me have this, please. Right. Okay, so as we go across the periodic table, there is a trend. A trend is, you know, we see an increase or a decrease. As we go across the periodic table, it gets harder and harder to take electrons from elements. So I had no trouble taking the electron from you. You didn't even know I was coming, so I just took it. You were like, what happened? And you was a little resistance. You overplayed it. I liked that. I think he was asleep. And then you strongly resisted me. And that is directly in line with the periodic table. Which elements do you think would be really hard to take electrons from? The noble gases. That's why they don't react. So it's really hard to take electrons from the noble gases, and it increases as it goes across. It increases as it goes that way. So these elements are really easy to take electrons from. The alkali metals, really easy to take them from. And the reason it's increasing is every element, let's go for like the third period here. every element in this group, in that period, I mean, has 1s2, 2s2, 2p6, and then they have this outside layer, that valence electrons, the outside. So they all have the same inside. And what do electrons do to other electrons? Repel them. True? So let's imagine for a second that I am the nucleus. What charge do I have if I'm the nucleus? Positive. And then you all represent energy levels. So Natalia, you're energy level 1. You're very close to the nucleus. She's negative, I'm positive. There'd be a large magnetic or Coulombic attraction. You're the second energy level, right? What's between you and I? And if she's electrons, you're repelled by her, aren't you? But you are still pulled by me, so there's like a balancing act between the repelling and the pulling. And then we have another layer of Minu. Minu, there's 2 layers between you and I, aren't there? And you find him repellent, you find her repellent, and even though you're being pulled to the nucleus, you're being repelled a lot, you're on the 3rd energy level. Then we have another one. You have 3 layers repelling, don't you? And then we have Ethan back there. Hey, Ethan. All of these people repel you. I can tell by your face they do. And they repel you, repel you, repel you. And so if another element, imagine I'm still standing here, if another element tried to take an electron from him, it's going to be easy because he's repelled, 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 repelled. These electrons are being pushed away, aren't they? So they're going to be easy to take. If the atom is small, though, let's say the atom is just me and her. Is there anyone repelling her from the nucleus? So it's going to be hard to take an electron from just one layer because there's no repelling. But as you add layers and layers and layers and layers, or energy level, energy level, energy level, energy levels, it becomes easier. So as we go down the periodic table, we keep adding energy levels, and the easiest element to steal electrons from would be right there. Who is that? Atomic size, actually, I always feel like we should do atomic size first when we teach this stuff. As we go across, the size actually decreases, which feels completely wrong to people. As we go down, it increases. And I'm going to try to give an explanation here. We just said we have like these 5 layers of energy levels, right, with Ethan in there. And so where would we be? Let's see. 1, 2, 3, 4, 5. So this is the Ethan level. There's 5 layers of electrons. And all of these inner layers, the 1s's all the way to the 4p's, would be repelling that 5th energy level. But is there any change between 1s2 and 4p6 as I fill these elements up? They're all going to be the same, aren't they? So everything in here has the same amount of electron repulsion inside. What happens to the number of protons as you go across, though? It goes up. And so those protons are pulling and pulling and pulling, and they end up pulling this layer in. As you go across, which element in the 5th level, the 5th period, has the most protons? Xenon? So xenon ends up being the smallest in that period because it pulls its electrons in. And then rubidium ends up being the biggest because it just doesn't have as much protons. And that there's a term for that. It's called the effective nuclear charge. We don't using that term. We're just kind of looking at the trends, not trying to necessarily explain them yet. And then the last trend we're going to look at, and then we're done for sure, I think, is shielding effect, which I've actually already explained, so that the inner energy levels shield the outer ones. They're shielding them from the nucleus. So if I am a xenon atom, I have 54 protons. My 54th electron is way out there in the Ethan level, and that 54th electron is repelled by these 2. It's repelled by these 8. It's repelled by these 8, these 16. And these electrons are way far away. It's actually more than 16. Way far away. Oh, 16s, right? And they're going to be shielded from the nucleus by the inner electrons or core electrons. As we go across, shielding effect is the same. As we go down, shielding effect increases drastically. It's the same as we go across because you have the same number of electrons on the inside. But as you go down, you're adding layers and layers of electrons. I lied. We have one more, don't we? Electronegativity. So, two elements come up to each other. Here we go. Ready? You're an atom. I'm an atom. Two elements come up to each other, and they start pulling on each other's electrons. Immediately pulling. I want your electrons. You want my electrons. I want your electrons. You want my electrons. And the pull is based on how many protons I have, and it's based on how many electrons are between me and the outside. If I have like 12 layers of electrons, which is impossible, that's a lot of repulsion. And therefore, I'm going to be like, I want that electron, but I'm already full. And I can't take it. So every time two elements come together, they start to pull on each other, with one major exception. So as we go across, it starts increasing drastically. Except for what, do you think? The noble gases. So it's like increasing, 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 increasing. Zero. There's no attraction to your electrons. None. And as we go down, it decreases because of that shielding thing. The electrons keep getting farther and farther and farther from the nucleus, so they're not going to have as much pull. Increases as you go across until you hit the noble gases, and then it stops. Decreases as it goes down because you're adding layers and layers and layers of electrons. And I think that that's the end. We do have a polyatomic ion quiz next class. Very simple quiz. I'll have these symbols written down. You write those names. No big deal.